Hello, my name is Gonzalo Abad, and in this tutorial we are going to do symmetrical voltage dips analysis in a wind turbine based on DFIG induction generator. All the information related to this topic can be found on those two books. There are 2 or even 3 chapters related to this topic, or even in this book, in which chapter 10 also is related to this subject of voltage dips. All these books have been edited by Wiley. So first of all, we need to use the Simulink program that we have been using in previous tutorials. Let's open it. Here it is. And what we will do is just perform here voltage dips, symmetrical voltage dips. And we will analyze what happens in the entire system, wind turbine, generator, and back-to-back converters, and what can we do from the control strategy point of view and hardware implementation point of view. So if we go to chapter 10 on the second mentioned book, here in page 45, we have one analysis related to voltage dip. It is very recommendable to work with the equivalent circuit of the DFIG induction generator represented in this way, and at a steady state and normal operation conditions we have this phasor diagram. What happens is that when we have a voltage dip, let's do it smaller, this stator voltage that was in normal operation is reduced suddenly to a much more smaller value. The thing is that this stator flux cannot evolve rapidly to a very small value. Therefore, in order to keep this voltage, which is this voltage, and is an image of this rotor current, in order to keep this voltage small, we would need a big rotor voltage. And what happens is that normally the back-to-back converters are not dimensioned with such big voltage. Therefore, we normally lose control. So in order to avoid this problematic issue, what we normally do, the solution for this problem, is to put a protection here, which is normally called crowbar protection. There are different hardware crowbar configurations, but most of them are equivalent, which is, and I have chosen in this case one diode bridge, one switch, and one resistance. And what we do is put a resistance in each terminal of the rotor. So thanks to this, what we can do is make this flux, this stator flux evolution during the dip much more faster, and reach the new steady state with the reduced voltage at the grid and therefore at the stator much more faster. This is what we are going to do. So let's go to the Simulink program, and the first thing that we are going to do is just create the voltage dip. So by this voltage source we can configure several features here. So first of all, we are going to create the voltage dip, for instance, by including a harmonic, which is going to be the fundamental. Yes, and here we will put 10 times bigger, phase shift 0, and this is going to be a positive sequence. Then for the second harmonic that we can put, this is going to be 0 and 0. So we won't use this one in here. And the voltage dip, this voltage is going to be from 0 to 3, for instance. So after time second 3, we are going to make disappear this part, and therefore the voltage, the remaining voltage that we are going to have at the grid is going to be 0.1. So this is going to be the voltage dip, a voltage dip of depth 0.9. And then we will create a recovery, for instance, with a ramp of, yes, 15 per unit per second, and the variation time is going to be 3.5 until 4.17. So with this, we will start recovering the voltage at second 3.5, and we will recover totally the voltage at this 4.17 seconds with a ramp of 15 per units related to this value per second. And the simulation that we are going to perform is up to 4.4. So what we are doing with this is just create the typical voltage dip profile like this. Okay. So once we have this, we will make a little bit of a space for including the crawler protection. Let's do this something smaller. We will need just to copy a power converter, and here we will choose diodes. Diodes with the normal set conditions. Yes, this is A, B, and C. Then, as we have seen here, we need a switch and we need a resistance. We need a resistance that, for example, we can take it from here. R crowbar, and here we will choose branch current in order to be able to see it, to visualize it later. Then here we need a switch, so we need to go to Simulink library, Simscape, Power Systems, Specialized, Technology. We open them, fundamental blocks, and here I think that it is in this block. Let's wait. We will choose, for instance, an ideal switch. So we remove the name, we make it smaller, we just left the normal parameters. Yes, let's do bigger, and let's connect it to our crawler protection. Yes, so that's all. So now we need to control this element. So let's have a look. We will need from Simulink library again. We will use blocks like sources, and we will use a step, the step block. So we copy it from here, we make a group with it, we eliminate the name, sorry, so we eliminate the name as always. Sorry. And we can connect it to the switch. Then we need to know when are we going to connect it. Let's do it smaller. Let's move this lower, down. Okay, so this is the step. We eliminate the name, so now this block is match, clean and clear. Okay, so we have said that we are going to, we have said that we are going to perform here at time instant 3 seconds the voltage dip. Therefore we need to activate this crawler at this time. But before we continue, let me find here this block. I copy it and I will put it there, and I will use another step. So at time 3, initially it will be 0 and then it will be on, value 1. And once the voltage dip per turbines has been overcome, let's say that will be at time instant, for instance 3.1, after 100 milliseconds the voltage dip, what we are going to do is, yes, -1. So with this -1 plus this one, here it will be 0. The detection should be made automatically, but here, as we don't have time to create everything automatically, because this video tutorial will be too long, I will do it in this way. So our objective is to left the crowbar operating between time second 3, which is the initial moment of the voltage dip, and 3.1. In reality, we should detect ER, the rotor current, bigger than ER limit, and, or better said, the DC boost voltage should be bigger than the limit. So in reality, the perturbation caused by the voltage dip can be detected by one of these two events. The first one that happens will activate the voltage dip, the crowbar protection, and this should be made automatically by checking these two variables. Normally, this current is the first one that crosses the limit, and this is very few milliseconds. 1 or in 2 milliseconds, the rotor current has been has made very big. Okay, so here we have the protection, and now we need to do some things at the control, more specifically at the rotor side control, which is here. Yes. Once the voltage dip is detected, the crowbar protection is activated, and then by means of this resistance, the stator flux has been damped very quickly, what we have said that we need to do here with this stator flux, and this can be seen here. This will be the normal damping of the stator flux, and here will be with a rotor resistance included by means of the crowbar protection. Once we have done this, now we can operate again this control, the rotor side control, but in general the grid codes tell us that we need to provide all the current that we can reactive current through the grid side, and this is made by IDR reference. So let's take a step from here again. So we don't need this anymore, and we will include this step here. Let's remove, as always, the name, and we connect it there. So here we are going to provide the total current, the rated current at time instant. For instance, we have said that at 3.1 we are going to disconnect the crowbar, so let's do some milliseconds later, 3.15 for instance. So initially we have 0 for this reference, and then we will provide the total amount of current. What means, if we go to this, and if I'm not wrong, to page 13, no. Yes, to page 13. If we check this formula, we are providing as much current as we can here. Therefore, we are providing, if we put this value in positive with this negative value, we are providing reactive power in negative value as demanded by the grid codes. Okay, and as all the current is going to be at ID, at IQ, we should do something, which is eliminate this current. One simple way to do it is just copy this and put it there. Okay, now I need a multiplier, so let's find it here. Math operations, probably. Yes. Here we have the product. Eliminate this. So now we need a little bit more space. Let's do some space here. And here. And here, probably at the input, it should be at the output. It doesn't really matter. Okay, so we are going to multiply this entrance. Let's do it something smaller. Here and here. This is the reference, and this is the block. And this is still IQ, and this is still here torque. Yes. Okay. So when do we need to make zero this current? We will need to make zero this current when we start providing IDR, which is this time instant. I copy it. So initially it will be 1 and then it will be 0. And when it's going to finish all this, that will be, as we have said before, once we recovered, yes, that will be 1. Once we will recover totally the voltage, that it will be at time instant 4.70. Okay, and once it happens that, we will need to make 0 again IDR. So here again, we don't really need 2 steps. We don't need 2 steps. We will need to make, we will need to make 0 this current at 4.17. Initial value 1 and final value 0. Yes, I think it's correct. Just keep in mind that here there was the maximum power point tracking, and this is the torque reference. So we need to manage with these 2 currents, ID and IQ. So during the dip, yes, all the current is going to be provided by ID, and this will be 0. Obviously, this means that we won't have torque control of the wind turbine, which is a little bit risky. Okay, so I think that we have everything. Let's move all this to the left so we have some more space. Sorry. Yes. Here you go. Okay, so we can save it. Yes, so once we have this, we can go now for the monitor block to visualize the different variables that we want. Okay, so let's copy, for example, yes, this element down here. Sorry, didn't work. Let's move more. Yes, there it is. Let's do it bigger. And this is going to be fold. So maybe it's not possible to see it. So let's move it there. Fold. Analysis. And we will use 2, 4, 6 elements. Therefore, let's use here 6 with a layout of this shape. And here, before continue, we need to take this crowbar current before we forget it. So I will need the multiplexer from here. For instance, we were here we are. One, 2, and we need to select it. Let's wait. This should be the other one. Okay, there it is, and this is going to be, sorry, yes, now it's connected. The crowbar. This is going to be the current. Let's eliminate all of those. Let's remove what we don't need. Okay, so here we will put UVs, the stator or grid voltage, because always is useful to see it. So let's put it there. This is VS. Then we will use the rotor flux, that we can call it, sorry, FS. That will be the second one, FS. And this should be taken obviously from the measurements of the generator. So we need to choose it. We need to select from stator measurements, flux, stator flux, select, and stator flux. Okay, so now we have another 2 outputs, and let's calculate directly there by using one function. Where we're here. U2 square. So here we calculate the amplitude of the stator flux, which is enough for visualization purposes. And we need a multiplexer. Probably we can take it from here, copy, and paste. Connection and connection here. Okay, and this is going to be, as we have said before, FS. Yes, and this comes directly through here. Then it is very recommendable to see, we don't need this, the rotor current. Therefore, let's see it there, and that will be the third. So this is here. What else? Let's put here, for instance, a crowbar, the crowbar current. Yes, this one, and let's call it I crowbar. What else? Yes, then let's also visualize at this monitoring the stator current, because it will be useful. So here we put IS. Yes, and finally let's also check what happens, sorry, I didn't connect, with the torque. Just visualize the actual and real torque taken from, sorry, let's put it there, sorry, let's put it there. This is the torque. Okay, so this is the other element that we have placed it here, so we can make some space here and here. In normal operation, we can see the typical two scopes of the rotor side control and grid side control, and when the fault analysis must be done during the voltage dip, we can see this other scope. Okay, so once we have this, we go to the initialization program, and what we left is to give one value for this crowbar resistance, the protection. Let's put it at the end. And let's give one value of 0.2 ohms, for example. And let's see now what will happen. 0.2. Yes. Okay. So let's initialize the system. Yes, working okay. This is our program. So now we can run the simulation, but before doing it, there is one important thing missing. When the crowbar is activated, the rotor and grid side converter must be protected, so the current shouldn't go through this way. All the current, all the energy should be burned in the protection. Therefore, we need to disable the rotor side converter, so let's do it in this way. We need a multiplier. Let's take it from here, for instance, copy and paste, rotate, and inhibit just when the crowbar is activated. So at time instant 3 should be disable the rotor side converter, yes, final value 0. And once the active crowbar is disabled, this rotor side converter, after 100 milliseconds, this rotor side converter should be enabled again. So this is, in reality, in the real wind turbine, it should be made automatically, but in this way in this case we are doing in this simple way. And then finally, before start the simulation, let's put it here, less wind, so we have to wait less time. Okay, so we can save now. And before we start, let me close this program, and we will use the accelerator in order to do the simulation faster. So let's simulate. We need to compile, and we need to wait some few seconds before the simulation starts. So let's wait. So now it seems it is working, it is simulating. Yes. As always, the startup of this wind turbine based on the DFIG induction generator that we are doing is not made as we should do in reality, but as we don't want to do a very long tutorial, we are doing the startup in a very simplified way. Here we can see that we have a very big over voltage at the DC bus voltage, and due to a huge amount of power that is coming at the startup through the rotor. But anyway, we forget about the startup process. Here more or less we see that the grid side converter is now working. The current loops seems to be okay, and the DC bus voltage is oscillating but reaching the steady state as demanded by the reference, 1150 volts. Here the rotor side converter and control is also seems to be working properly. Just remember that at second 3 we have programmed the voltage dip. So now it's going to happen. Here it is, the sudden voltage variation, and here is the crowbar activated. Now it's disactivated after 100 milliseconds. Everything is going very fast. The stator flux has gone down from one value near to here, and now we are at the voltage. And now the voltage recovery after the dip is happening, and therefore also we see how the stator flux is taking also its rated value according with the stator or grid voltage. During this time, obviously, the crowbar protection is not activated. There we have the simulation. Almost finished. Yes, finished. So let's have a look at what has happened more carefully. So the voltage dip that we have programmed is at second 3, so let's forget about the startup and let's focus what has happened after second 3 more or less. Let's do the same here. There it is, and let's do the same here at the fault analysis scope, more or less there. Okay. Let's do some zooms in order to see with better details. Yes, and the same for the grid side converter. Okay, so at second 3 we have performed the voltage dip, and the remaining voltage at the grid is only 10% of the normal voltage. As we have programmed, once the voltage dip occurs, suddenly the crowbar protection is activated, so all the current, all the energy goes through the crowbar. This is the current, and just keep in mind that by changing the crowbar resistance we could do this current peak bigger or lower, and also this current variation faster or slower, what means that we could make the flux reduction faster or slower. Then during this crowbar activation we see how all the rotor current goes through the crowbar protection, and the rotor side converter is protected. All the current goes through here. And during this time also, the crowbar activation, during the time where the crowbar activation is present, the stator currents are very high and we cannot control them, we cannot do anything about it. And then also during this time, during this crowbar activation, we have a big torque peak in which very much related to the crowbar current peak, which cannot be avoided. Then if we see the rotor side converter performance, here we can see how at the beginning we have made, at the beginning of the voltage dip, we have made the Q component of the current 0 after the crowbar activation, and therefore the torque is 0 as well, where it's 0 in its mean value, but there are oscillations due to the voltage dip. And therefore, here what happens is that as the maximum power point tracking algorithm is requiring this torque in order to control the speed, just remember that here we have the maximum power point tracking control working. What happens is that the speed, we lose control to the speed, and therefore the speed, the rotational speed, is modified, and in this simulation there is a quite big speed variation. In reality, we should have more inertia that we have performed much bigger than this value. Therefore, this rotational speed variation should be smaller. Then during the voltage dip, as demanded by the grid codes, we have performed a high value of ID rotor current in order to provide reactive power through the stator, through here, by imposing the component of the current here. That, if we go to the theory, if I'm not wrong, page 13, yes, here we have the equations. This is the ID current that we are putting, and just keep in mind that this stator flux, due to the voltage reduction, has gone down. Therefore, the reactive power that we have is also, the availability of reactive power is less. What we can put is here just reactive current. Here they are, the rotor currents in ABC. Yes, then also, if we should make this variation lower because it is problematic, we know that we could manage these D and Q components of the current in a different way, and what we could do is don't make zero this current. Again, checking the formula, as we are with less flux here, with a given component Q of the current, we have less capacity of doing some electromagnetic torque. But anyway, instead of doing zero here, the torque, because of we have made zero the IQ current, we could follow in some way to the torque reference demanded by the maximum power point tracking. And this is more or less the behavior. Here we have the stator currents. If we see here one very small zoom, what happens here? Yes, more or less, if we recheck the yellow one and the yellow one, here we see the phase shift between the voltage and the current more or less 90 degrees, which means that we are providing reactive power, reactive current. Sorry, I have lost the simulation. More or less, we were here. Yes, that's it. And that's it. And then here at the grid side converter, what we see is that the voltage dip has provoked some DC boost voltage variation, but nothing very important, because the grid side converter is able to work properly with this voltage dip that we have programmed. It has to be remarked that in reality, as demanded by the grid codes, we should provide a huge amount of reactive currents, so we could also do it, by means of the grid side converter, by providing during the dip here, for instance, a reactive power reference negative. Here in this case, in this simple simulation, we haven't done it, but we could do it. So summarizing, let's go back to the program again. Summarizing, we have included a protection, a crowbar protection that is suddenly activated when the voltage dip occurs. We have done it by simple steps, because we knew when it's going to happen, but this should be made automatically in reality. When the crowbar is activated, we need to disable, we need to inhibit as well the rotor side converter in order to protect it. And then what happens is that we burn all this energy at the crowbar resistance. We can make this event faster by putting a resistance which is lower, but that will mean that this current peak and this torque peak will be bigger. So depending what we are demanded by the grid codes, the speed or the fast that we need to be, we need to carefully choose the crowbar resistance. Then once the crowbar resistance, the crowbar protection, is deactivated, we have control again of the rotor side converter, and what we need to do is manage with the D and Q components of the currents. In this case, what we have done is put or set all the current at D component in order to provide reactive current or reactive power through the stator, through here, by means of this current. And therefore, what we have done is put at zero, the Q component of the current, which means torque. Therefore, we have made the torque 0. As the reference is this one, given by the maximum power point tracking, we have loose control of the rotational speed, and we have had in this simulation this speed variation. In reality, we could have less variation because the inertia that we have normally is bigger than in this simulation that we have performed. However, if this speed variation is still too big, we could make this torque different from 0, and we could manage the current between D and Q components of the current, not following totally the torque reference, but a little bit less. And during all this time, the grid state converter has been working properly. Then also, just see how once the voltage at the grid is totally recovered, we have again control of the Q component of the current, and we provide the torque demanded, in this case this one, by the maximum power point tracking algorithm. What means that we have control again of the rotational speed, so it begins again to go down. And in this case, we have set the D component of the current to 0 as well. Yes, one last thing to mention. Just during this time, when the crowbar is activated, during this time we didn't do nothing with the PI controllers of the current regulators. In order to perform a better transient, this transient that we can see here and this transient that we can see here, this one in here and this one in here, we could manage also with the integral action of these PI controllers, but we didn't do it because it is not so important here. That you can see that this was not so bad in terms of current peak. Okay, so that was all. I know that this topic of voltage dip is not so simple and easy to follow, but I hope this video tutorial was useful and interesting for you. Thank you for your attention.